For the second part of example 2, we're told that there is going to be a point between the wires where the net magnetic field is 0. And we want to know how far from the bottom wire that point is. There's actually going to be a line. So let's draw the wires again. So I have a current I2 that points to the right, a current I1 that points to the right. Now if I draw this from the head-on view, so I've got I2 coming out of the board, I1 coming out of the board. Let's just pick some point in between these and consider the direction of the magnetic field due to each. So let's look at this position here. So to determine the direction of the magnetic field, I point my thumb in the direction of the current, and my fingers curl around the current in the direction of the magnetic field lines. So for I2, I would have a field that points like this. For I1, I would have a field that points like this. Now, as I get close to I1, its magnetic field strength increases, and I2's magnetic field strength decreases, and vice versa. So I can imagine that there is some position here, right, if I go up or down, where I'm going to find that these two magnetic fields are the exact same, they have the exact same magnitude, and since they have opposite directions, that means they would cancel. And then if I looked at this figure over here, that would actually occur along a line. And what I want to know is how far from the bottom wire does that happen. So let's call the distance from the bottom wire x. So, again, it's probably easiest to look at it from a head-on view. So let me redraw this head-on view. And let's assume that we know where this position is. It doesn't matter if we know where it is. We're just going to call the position a distance x from the bottom wire. And we know that the magnetic field due to current 2 is going to point like this. And we know that the magnetic field due to current 1 is going to point like this. So the distance that current 1, I've drawn current 2 twice. The distance from current 1 to this position would be this length here, and that's going to be the distance between the two wires, which is d minus this distance x. So if I just draw a coordinate system so that I have some reference to write down these magnetic field strengths in, I have two magnetic fields that have only x components. So let me write down the magnetic field for 1 in this coordinate system. It is going to be U0 I1 over 2 pi, distance from the current to the observation point, which is d minus x, and that's a plus x direction. And for I2, it's a distance x from the observation point. It points in the negative x direction. So B1 minus, or excuse me, I should say B1 plus B2, if I add them together as vectors, that should be equal to 0. So if I look at just the x components, I will have the x component of B1, which is plus U0 I1 over 2 pi d minus x, minus plus the x component of B2, but that's negative, so it's going to be minus this, and that's equal to 0. So let me cancel the terms that are the same in both. This is going to be I1 over d minus x minus I2 over x. Alright, so the physics is basically done now. We just need to do some algebra. What we're looking for is that distance x. We want to know how far from the bottom wire this position is. So I just need to solve for x. Let me move the I2 over x term to the other side. Now I can invert both sides. Note that in general I can't just invert this and invert this, right? Now they're equal, the sum of these two, or the difference I guess, is equal to 0. So in this case I can, it's essentially going to have the same effect as inverting both of them. But in general I can't just take 1 over the right hand side to be 1 over each of the terms in this difference. So that'll be d minus x over I1 is equal to x over I2. Alright, so I'm going to have an x over I2 plus an x over I1 is equal to d over I1. Factor out the 1 over I2 plus 1 over I1. And I'm going to combine these two fractions. And now I can solve for x. There's a I2 in the numerator and the denominator. But wait a minute, that doesn't seem right. What did I do here? Okay, so I'm going to go back up to here and look. Factor that out. I had an I2 sneak in under D. That should be an I1. So this should not be an I2 down here. It should be an I1. And now it's the I1s that will cancel. And that will leave an I2 up here. All right, there we have it. So this is the distance from the bottom wire, which is current 2. And we can do a couple of things to check to see if this makes sense. So let's imagine that we had two currents. We have I1, I2, and let's assume that I1 is equal to I2. Well, then we would expect the magnetic field to be 0 at the point exactly halfway between the two currents, right? Because they're going to have, from the same distance away from the two currents, the magnetic field strength would be the same if these two currents are the same. And so if we plug in I1 is equal to I2 for x, we get x is equal to d over 2, which is exactly what we expect, halfway between the two currents. Now let's consider if I1 is equal to 2 times I2. So if I1 is equal to 2 times I2, then we would expect the magnetic field due to I1 would be stronger at the halfway point than I2. So we'd have to move closer to I2. So we would expect, so this is the halfway point, let's say, if the two currents are identical. What's going on? Oh, there we go. So if the two currents have the same magnitude, we would expect the field to be 0 at the halfway point. If I1 is larger than I2, then we would expect the 0 points to be somewhere closer to I2. So let's plug in I1 is equal to 2 times I2. We keep the I2 up here. I'm going to replace I1 with 2 times I2. And that's going to be d over 3. So this is d over 2. D over 3 would be down here. So that's exactly what we expect. So we can, at least check to make sure that our result is consistent with what we know should be true, and it is. So that gives us some confidence that we've got the right answer.